Could there be life on other worlds? Scientists look to Mars and the asteroid Bennu for that answer. You're listening to Are We There Yet?, the radio show exploring space exploration. Hi, I'm Brendan Byrne. It's a question long asked. Could there be life outside our own planet? The Mars Curiosity rover may have found evidence of just that by finding molecules that could be linked to life. We'll speak with University of Florida's Amy Williams about what the rover found and how it is looking for signs of life on Mars. Then we're talking about another life-finding mission at the asteroid Bennu. The mission to the asteroid returned with samples back in 2023, but now a closer look at what was found has come to the surface. We'll speak with University of Arizona's Andy Ryan about the mission's success and surprises. That's ahead on Are We There Yet? Scientists have always asked whether life is unique to just our planet. In a new study, the Mars rover Curiosity may get us one step closer to answering that question by finding elements that here on Earth are the building blocks of life. But even if the findings link to life, it may not actually be because of life. And the only way we can know is to look at it more closely and maybe bring these samples back here to Earth. Here to talk about the findings and how the Curiosity rover made this discovery is Amy Williams, an astrobiologist at the University of Florida and a scientist on the NASA Curiosity and Perseverance rovers. Amy, welcome back to Are We There Yet?
Thank you so much for having me on.
One, you found new organic compounds, and two, you found them using a brand new way to do it. So let's start with the method first. With these new findings, how did you actually go about finding them?
The project this has been sort of my career with the Curiosity mission and the SAM instrument. So it's, first, I just have to say, a labor of love and science to finally have these results coming out to the community. We used a new technique that's never been used on a flight mission before. It's a process called, get ready for it, take you back to school, thermochemolysis. The way to think about it, it's just a technique that you heat up a sample and you use a specific chemical with it. That's the thermo-chemo part of thermochemolysis.
Oh, okay. I had you with the thermo. I did not know the chemo part, but thank you. Okay, so,
no worries.
So heat
Yes.
and chemicals.
And so normally we just use heat. This is a new chemical we had not used on any flight mission before. It's called TMAH, and I won't even bug you with what it stands for. But the chemical is really powerful in that it's able to break apart larger, what we call macromolecular carbons. So picture, it's almost what the material is that makes up sort of like oil and gas, but it's not necessarily from life. You can make it abiotically.
Gotcha. So tell us a bit about the SAM instrument itself and how you're going about making these findings or pulling off this experiment.
The SAM instrument has 74 sample cups inside of this little carousel, and we normally deliver sample to a cup that is lifted into an oven. You heat up the sample, and that's how we get the organics out as gases for our gas chromatograph mass spectrometer, which is the instrument, one of the instruments on board SAM. And this experiment has a cup that already has that chemical in it, TMAH. So we puncture into the cup, release the chemical, dump the sample in, and allow it to react with the chemical before heating it up. And so in this way, you're able to get sort of a different flavor of the organic molecules that are preserved in these rocks on Mars.
I imagine it's just like you are in your lab mixing beakers worth of stuff, but you're able to do it remotely on the Curiosity rover, right?
We literally do this in the lab all the time, and my grad students can testify to that it is, adding a little bit of this and a little bit of that, and doing it autonomously and dealing with any, issues that ever arise when you have to do this autonomously. It's a pretty incredible engineering team.
So using this experiment, what did you find?
So we found a diverse suite of organic molecules, some of which we have not seen before on Mars. I can lead with the front line that you can't tell if it's from life or not. In fact, some of the molecules that we got from this experiment are the kinds that you would see forming on meteorites, honestly. So abiotically forming in the interstellar medium, and meteorites rain down on planetary surfaces all the time throughout sort of the history of the solar system. And so it's that material that probably was the seed stock for the origin of life as we know it, at least on Earth. And so you are seeing similar sort of feedstock falling on Earth and Mars. So I'm viewing this as a way of thinking about sort of the things that were falling to Mars early on in its history. These rocks are maybe 3.5 billion years old. So that's still a billion years after the planet's finished accreting. And so it's sort of a window into were the components there that could have supported potentially an origin of life, or like the original kind of precursor molecules to lead you to origin of life. It could have been organics that were available for metabolisms if there were ever microbes that originated on Mars. But what we found are these organic molecules that broke down from something that was what we call macromolecular. That's stuff that is much larger, and you need that thermochemolysis to break it apart and see its components. These little components of larger molecules. And we're able to see these, for the first time with this experiment.
What were the compounds that you found?
So we found 21 individual compounds at least. The spectrum is really busy. And so we spent a long time breaking out each one of these data points and trying to confirm what we thought we were seeing with the flight instrument by doing experiments in the laboratory and confirming sort of the mass of the molecules when they come out of the instrument. It's called the retention time. And this is how you would confirm the identification of molecules on Earth. We're just trying to do it with data sent from Mars. So the molecules that we saw are what we call aromatics. So these are circular or cyclic organic carbon structures. The ones that you people may have heard of are things like benzene or naphthalene. These are just ring structures. We did not see any of the hydrocarbons that a previous experiment did detect. But what we're seeing are these ring structures that kind of look like what you would expect to see from the organic matter that falls in from meteorites. So we saw a molecule called benzothiophene, which is a sulfur-bearing molecule, and it is pretty predominant in meteoritic organics. And so seeing that, kind of led us along the path of could some of this be from meteorites that had fallen onto Mars billions of years ago. One of the other kind of tentative identifications, we couldn't identify every single molecule, of course. But one of the things that we found really interesting was this molecule that is similar to precursor molecules that might have played a role in of making RNA and DNA. So we did not find RNA or DNA. We maybe found a precursor to that. So it's the step before life. We have not previously identified a molecule like that on Mars.
You're listening to Are We There Yet? From Central Florida Public Media, I'm Brendan Byrne. We're speaking with Amy Williams, an astrobiologist at the University of Florida and author of a new paper that found new compounds via a new method of exploring using the Mars Curiosity rover. Amy, the fact that these molecules were there at the time that you think you are, does that give you a sense of what the environment was in Mars's past and if it could, in fact, harbor life because these molecules are there?
We think meteorites might have played a role in delivering some of that organic carbon. It really is hard for us to say whether it was endogenous to Mars, right? If it's formed by geologic processes or maybe even by biologic processes, we really can't say. But we can kind of pick apart some of the more likely options because, of course, we want the highest level of evidence to say anything about life on Mars. What I find very exciting is that you do see organic molecules preserved in like the very near subsurface of Mars. We're talking less than 6 centimeters into the rock is how deep Curiosity is able to drill. And so we honestly expected organic molecules to be obliterated by the radiation environment on Mars, right? Even down into the subsurface to a certain degree. And so it's actually really exciting to see that complex macromolecular carbon like this is preserved. It's sticking around. We're able to detect it even after billions of years. So I think what we're getting from this is more of the story of how Mars was a habitable world in its ancient past, how we have all of the components that you need for life as we know it. We just haven't found that life yet on Mars.
And Amy, you and I have been talking about this for quite some time at this point. So I know this. I'm taking nothing away from your experiment done on with Sam on Curiosity, but we really need scientists on Earth here to confirm these results, right? Is that the next step?
I mean, it would be fantastic to be able to confirm with a variety of methods. And so that might be some point returning samples from Mars that we would be able to test on Earth. There's a lot more TMAH chemical on Earth than there is on Mars. In fact, there were only 2 cups of it on Mars, and now they are both used up. So yeah, having samples would make the world of difference. The really cool thing I think about this experiment is that it is actually the trailblazer for upcoming missions, not just to Mars, but actually also to Titan, that are going to utilize this chemical. And so we have the opportunity to use this as really a building block to searching for more complex carbon out there in the solar system, using this relatively simple technique.
That is very exciting for the future of Mars rovers and planetary rovers outside of that. Speaking of which, some news last week, the European Space Agency's rover, the Rosalind Franklin Mars rover, received a ride to Mars via Falcon Heavy, launching right here in our backyard at the Kennedy Space Center. Tell us a bit about this rover. Will it be doing similar experimentation?
Oh, it will be. And this is just the perfect segue. I'm beyond thrilled to hear that Rosalind Franklin has arrived finally. This is a mission that's been a long time in development, and I'm I'm so excited, for astrobiology missions to Mars anyway, and I'm extra excited about Rosalind Franklin because she carries on board basically the next generation of the SAM instrument. It's called MOMA. It's the Mars Organic Molecule Analyzer. And it has the capabilities of SAM times 2. We have a bunch of different ways to get at organic carbon. We have additional chemicals to perform these kinds of reactions. And of course, I'm excited because that chemical I just published on TMAH, it's flying on board Rosalind Franklin as well.
Very cool. And where's Rosalind Franklin going? Do we know?
So it's going to go to Oxyaplanum. This is a really ancient terrain. The Rosalind Franklin rover is unique in so many ways. One of which is that it carries with it a 2-meter long drill. We have, as I just said, we've drilled 6 centimeters into the subsurface of Mars, and I'm beyond excited to get down to those kinds of depths with Rosalind Franklin because we figured organic carbon would be destroyed near the surface. We're seeing evidence that you do have some of it preserved. And so the deeper down you go, you're actually reducing that damage from radiation. And so you may actually see far more complex organic carbon at depth. And so, this is really taking what the SAM instrument set up decades ago now and taking it to the next level, looking deeper into the subsurface of Mars, using a broader suite of instruments that may be able to help us address that question of whether there ever was life on Mars.
2 meters is something like what, 6.5 feet deep? I mean, that's
Yeah,
far
yep,
deeper
yep.
than where Curiosity is going, right?
Oh yeah, orders of magnitude. Curiosity, Perseverance drilling cores, it's still about the same depth of at most maybe 6 centimeters. But yeah, getting 2 meters down is going to be game
Wow.
changing.
And unfortunately for me, this is all happening inside the spacecraft, right? Because now I'm thinking in my head that its little arms have its beakers and its fluid and it's doing all that stuff right there.
I think that was the original dream, I think, for wet chemistry on the SAM instrument. But yeah, to automate something this complex, it is a little simpler than that at this point.
Yes. And your technique has been proven to work. Mine, probably not.
The next step is really, crewed missions getting to do these kinds of in situ experiments, which would be fabulous. And that's the next step beyond if you can return samples, man, if you can even send people to go do it in place, that's pretty exciting as well.
It is always a fun conversation with you. It seems like we're getting closer and closer to finally answering those questions about Mars and whether or not it did have life before. So Amy Williams is an astrobiologist at the University of Florida and a scientist on the NASA Curiosity and Perseverance rovers. Amy, thank you so much for joining us.
Thank you.
Still to come, a closer look at the asteroid Bennu.
We were expecting to find beaches, and we got there, and it was boulders all the way down. And so we predicted, based on the data we collected when we were at the asteroid, that, okay, these boulders must be weird in some way to have these thermal properties, because we got the modeling right. They have a low thermal inertia, but how? They're not like boulders that we had measured in Earth's laboratory.
Surprising samples. That's ahead on Are We There Yet? You're listening to Are We There Yet?, the radio show from Central Florida Public Media. I'm Brendan Byrne. What if one day you could stay at a hotel on the moon? As NASA and commercial companies ramp up their launch cadences and look towards living and working in space, tourism amongst the stars could shortly follow. From dining choices to transportation and hotels, space hospitality is something we could see in the next decades. We'll talk more about space hospitality and tourism next week on Are We There Yet? But for now, we're talking about Bennu. NASA's OSIRIS-REx mission launched over a decade ago, returning samples from that asteroid in 2023. The mission's main goal was to see the asteroid's composition and if its makeup could help answer questions about the creation of life in our universe. But while studying the asteroid, scientists were surprised that it was more bouldery than smooth. Here to talk about what that means and what the samples have shown is Andrew Ryan. He's a scientist with the University of Arizona Lunar and Planetary Laboratory and a researcher for OSIRIS-APEX. Andrew, welcome to Are We There Yet?
Thanks. It's great to be here.
Hey, Andy, I love talking about OSIRIS-REx because it seems like this mission is the gift that just keeps on giving. There's more and more stuff that we are learning about this asteroid Bennu. But first, before we get into all that, just give us a quick refresher.
So OSIRIS-REx is an asteroid sample return mission. It's a NASA mission and the United States' first asteroid sample return mission going to a primitive, what we call carbonaceous near-Earth asteroid called Bennu. So the spacecraft went to the asteroid, we orbited it for a time, analyzed it with our science instruments to understand its composition, start to hypothesize about its origin and evolution, and then ultimately collect samples, bring them back for detailed analysis in the best laboratories that the world's able to offer in order to unlock the secrets of the early solar system and potential origins of life, because these types of objects we now know they contain lots of organic molecules, prebiotic, no life, so I should be clear there, but prebiotic organic compounds that may have ultimately seeded the Earth.
It succeeded in that mission of getting to Bennu, making those observations, grabbing the asteroid, the dirt from the surface and sending it back. But one thing I remember when it first arrived at Bennu, you all on the science team were taken by surprise because of what it looked like. What was so shocking about when you finally got to Bennu?
Yeah, so when we got to the asteroid and we're getting closer and closer and closer, and it's getting bigger and bigger and bigger over a period of a few weeks, you start to make out more details, and we saw, wow, there's a lot of big boulders on the surface of the asteroid. Okay, this might make it a little operationally challenging to collect samples. And the closer we got, the more boulders you saw, until we realized the entire surface is covered in boulders and there are no smooth, sandy or pebbly areas that we had anticipated before going that are really what we designed our sampling strategy around. And we knew there would be some boulders. We suspected it's what we call a rubble pile, basically a second generation asteroid made of fragments of a broken up larger body from the early solar system, but the devil's in the details, and it was a big surprise.
Why were there so many boulders on there? And they were interesting shaped boulders too, weren't they?
Yeah. So we saw a diversity of boulders on the surface. There were two main types. There were the more abundant type are these dark, really rough, or what we call hummocky boulders, and then these others that are comparatively a little brighter, that are more angular. They have more geometric block-like shapes. So it comes down to how we made the predictions before we got there that it wouldn't be so bouldery. We used a couple of different techniques. One of them was radar. We used the way that radar reflects off the surface, and that indicated that the surface might be relatively smooth. But we also used temperature measurements of the asteroid. We extracted something called thermal inertia, which basically is really, it's a measure of how easily the asteroid heats up during the day and how readily it cools down at night as it rotates with the sun coming in and out of view. So objects that heat up really fast and cool down really fast have what we call a low thermal inertia. They have a low resistance to temperature change. And that's typical for fine-grained materials like dust or sand. Like the surface of the moon is a prime example of a really low thermal inertia object. Super hot during the day, and then at night it gets super cold. The converse of that is like a dense, bouldery surface, like what we think of when we say boulders, like, a boulder you might find on the beach, in California, the Rocky Coast, where they don't get as hot during the day and they don't cool down quite as much during the night. And so we measured Bennu's thermal inertia using the Spitzer Space Telescope, and we found that it had a relatively low thermal inertia, which normally means, okay, I think that's good evidence that there's a lot of, sand or dust-sized particles or even pebble-sized particles on the surface of the asteroid. There were other lines of evidence that I won't go into, but that was the main one. And so the sampling mechanism was in part designed around that prediction that when we got to the asteroid, we would find areas with fine pebble or sand-sized particles, little sandy beaches, as head of the OSIRIS-REx mission, Dante Loretto, likes to say. We were expecting to find beaches, and we got there, and it was boulders all the way down. And so we predicted based on the data we collected when we were at the asteroid that, okay, these boulders must be weird in some way to have these thermal properties, because we got the modeling right. They have a low thermal inertia, but how? They're not like boulders that we had measured in Earth's laboratory. And so one of the predictions was, well, maybe they're just full of holes and they're super porous to the point where they may even be really compressible and have all sorts of weird exotic properties. That was kind of our best attempt, our best hypothesis from the data we collected there. But we knew we would get samples and bring them back to the Earth and analyze them. So we said, okay, well, we've done our homework here. We've hypothesized. Now let's just wait for the samples to come back. And this was that opportunity. And we found that they are porous and they may be compressible, but really it comes down to the way that they're fractured, and they have these really dense, almost cellular crack networks that spread through them. And I could go into, what that's telling us and why they're cracked in that way, but that's the explanation. And it may seem in some senses a bit underwhelming, but it was really hard to get there. It was really hard to prove that this is indeed the explanation. They're essentially just extremely cracked. That's telling us a little something about their history. But looking forward, this is going to help us better interpret other asteroids before we get there in the future too. So now, when we look at asteroids through a telescope, we extract things like thermal inertia. We're going to be able to do a better job of understanding what might that asteroid be made of. And that's useful for science. And it's also useful for planetary defense. Like if one of those asteroids is on a trajectory towards Earth, if it's covered in boulders and the boulders are compressible versus non-compressible, or it's covered in sand, these are things we want to know if we're going to try to develop a mitigation strategy.
I have to point out, I think, Andy, you are the first person to use the adjective bouldery on this show, and I really like it, so thank you for that.
All right. Hopefully I won't be the last.
You're listening to Are We There Yet from Central Florida Public Media. I'm Brendan Byrne. We're speaking with Andy Ryan. He was a scientist with University of Arizona Lunar and Planetary Laboratory, a researcher for OSIRIS-REx and OSIRIS-APEX, and he's now with the company Astroforge. Andy, you mentioned there are two things at the end of that that last answer that I want to get into, and one is those cracks, right? How did they form? Because that was a mystery to you all as well, right?
Yeah. So we did a little bit of hypothesizing in the paper that was released on this subject because, to be frank, we don't know with certainty yet. We think that some of those fractures are very old and formed on what we call Bennu's parent body. I mentioned earlier that Bennu is a second generation object. So it's made of fragments that originally came from a much larger planetesimal or, a young planet that got broken apart in the early solar system. And so we think some of the cracks are old because we actually see mineral deposits in the cracks that were formed from liquid water, which you would have only found in the parent body when it was much younger, warmer. And there are plenty of other signs of evidence that there was liquid water flowing through that body before it cooled and solidified and eventually broke apart. But a lot of the crack processing probably came later, within the last millions to hundreds of millions years of its history. One of the key processes may have to do with thermal cycling on the surface of the asteroid. It's rotating every day in and day out for thousands, millions of years. And so you're heating and cooling those boulders and they expand and contract over and over. And that introduces stresses into the material that can be manifested as cracks that begin to propagate. The propagation and nature of those cracks and how tightly they're spaced has a lot to do with, that's getting into the details of the structure of the material. And we found that those two boulder types on the surface of the asteroid, we found corresponding to sample types in the return sample, have different microstructural properties. One of them is really conducive to these cracks forming in dense networks, creating that low thermal inertia. And the other type, the angular, blocky, or more geometrically shaped samples, don't produce fractures as readily, or they're just kind of clean cuts, like the rock will break apart and it's done.
So you're getting a sense of what the origin is of the surface that it's on by looking at those cracks. I seem to remember that around this time, when OSIRIS-REx was making its way to Bennu, there was another asteroid mission that happened, and I'm wondering, looking back, did that mission run into the same surprises as OSIRIS-REx did. And really what I'm getting at is OSIRIS-REx's geography kind of an exception to what we know of asteroids, or are we going to be surprised by pretty much every asteroid we take a closer look at?
So I'll start with the other missions. So the Japanese mission, Hayabusa 2, went to the asteroid Ryugu. They were a couple of years ahead of us in terms of timeline, and they ultimately had almost the same surprises we did because they were going to the same or very similar type of asteroid. It was also a carbonaceous asteroid, also a rubble pile, and it also was covered in boulders despite its low thermal inertia. And they brought the samples back and had similar challenges and puzzles to solve when they were trying to analyze their samples. So that appears to actually be common for this type of asteroid, these carbonaceous asteroids. So I do think we've learned something that can more or less be broadly applied to that class of asteroid. Now, there are other classes out there. There are those that we would call stony type asteroids. We will be visiting one, actually many people will be visiting one soon when asteroid Apophis makes its very close Earth flyby in the year 2029. It will actually be closer than some of Earth's geosynchronous satellites. It's not going to hit us, and I always have to stress whenever we talk about Apophis, we say, well, Apophis will not hit the Earth, but it's going to be an amazing research opportunity, and that is a stony rubble pile asteroid. The OSIRIS-REx spacecraft, which has been renamed OSIRIS-APEX, is actually going to go to Apophis. So we'll get a second asteroid under our belt there. So we'll probably learn a lot of very interesting things when we see Apophis as a stony asteroid. Metallic asteroids are out there, and those have not really been visited much at all. There's the Psyche mission, which is going to an asteroid also called Psyche, and that's a very large, potentially metallic asteroid that's on its way right now. It's a NASA mission. And the company that I'm working for right now, Astroforge, we're aiming to go to much smaller metallic asteroids to basically try to mine them to extract precious metals. And I can guarantee you we're going to have surprises. So TBD, we'll see.
Surprises are always great in science, right? Yes. We've been speaking with Andy Ryan. He was a scientist with the University of Arizona Lunar and Planetary Laboratory and a researcher for OSIRIS-APEX. He's now with the company Astroforge. Andy, thank you so much for joining us.
Thanks. It was a pleasure.
That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Do that on Apple Podcasts, Spotify, or wherever you get your podcasts. Stay connected with the show. Follow us on social media. We're on Instagram and Facebook. We're at AWTY_Space. And if you got an idea for a future episode of this show or you want to join us as a guest, reach out. We're at arewethereyet@cfpublic.org. Are We There Yet is a production of Central Florida Public Media. Our intern is Orion Boone. Our producer is Marion Summerall. Editorial guidance comes from LaToya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.